Okay, ladies and gentlemen, appreciate you coming at 8:30 on a Monday morning. It's not the usual time for defense, but I think it's actually, it's really nice to have a full committee in person, which hasn't been the norm for the last...
You can blame me for that.
That's all right. I'm glad you're here. So, as always, these are master's defenses. In this case, João is a Brazilian Navy officer. He's actually a long line of people we've been lucky to have, both here at UNH and actually dating all the way back to UMB, going, they're all commanders and now left the Navy and stuff like that. But we've had a tremendous opportunity. João, as with all the other ones, went through the Naval School, the Naval Science School in 2011. He's been with the Hydrographic Service, got his Cat A in 2014. They've all arrived with Cat A. We've all arrived with an incredible amount of field experience. In fact, in 2020, he got a degree in production engineering from UFF. So I don't know if the Navy sponsored you or allowed you to do that. No.
No, not sponsored me, but
yeah. Allowed you to do that, yeah.
USF?
UFF.
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 Yeah, in Rio.
In Rio, yeah.
And the DHN, Department of Hydrography and Navigation, there has a broad experience in not just hydrography, but also in oceanography as well. And so João will be giving obviously his thesis defense presentation, and it's actually something that's very useful for me. I've been teaching about phase measuring bathymetric sonars for years, but never really acknowledged the change that happened about almost a decade ago now, actually, with EdgeTech, and we've never really understood. So this was an opportunity for João. So at that, I think I'll pass it over to you to provide your thesis presentation. Thank you.
Thank you, John, for your introduction, and thank you all for being here. It's an honor to present you my research and exploration of conventional beamforming applied to phase measuring sonars. So we have a great problem there in Brazil. We have long rivers in the Amazon, for example, the Amazon River, which is known by everyone. We have almost 10,000 nautical miles in a place where people depend on the rivers to survive, because there aren't any streets, so that they can get food, they can get medical assistance, and so you can see the importance of navigation there. So a problem we have there is that the river has a heavy sediment transport, and due to that, sandbanks move everywhere, and that makes the navigational risks quite high if you don't prepare for them. Here we have these red dots here are points where ships run aground because of this movement of sandbanks. So there you can see how important it is to update in a high rate there in the Amazon basin. Here we have two rivers, Negro River and Solimões River, that show you that we have there different types of rivers, not only sandy ones. This black one has, for example, it has a rocky bottom. So we not only need the TVU, but also resolution, and we also need target detection. And as we need an efficient system to have really fast surveys, we can think about the multibeam. This is a traditional one, at 60 degrees incidence. We can get at 10 meters depth, at 35 meters swath, which is not so much. As we're in shallow water, we may reach a little more with the multibeam, maybe up to 70 degrees, which is 55 meters. But if we can really make use of the PMBS, which are the phase measuring sonars, we can see much further. For example, if we can see up to 80 degrees, we can reach almost a double swath when comparing it with a 70-degree multibeam. And if you go really wild with the PMBS, you can get data up to 85 degrees, but obviously we need to assess the quality of this data. Naturally, we have, by using this long aspect ratio, you can see the picture is in scale. Now we cast these shadows. Obviously, we don't have bathymetry there, but we are sure that there's something there. So we have good target detection capability. Here we have some data that I collected. You can see here that I set 100 meters for each side, but however, we only get complete coverage up to 130 meters. This is a 10-meter depth area. The gray line in the middle is like the multi-beam counterpart. You can see that we have only 60 meters of coverage. So more than double the swaths I got with the 6205 here from the university. However, what hindered us from using the PMBSs all over the time is because of this historical problem here. We have the nadir gap that usually are brought because we have interference on nadir. The signal coming from the other side of the swath, making us to reject a corruption in the phase and making us to reject the nadir information. And how was this research born? It's because, as John said before, EdgeTech released this system here, the 6205, that the university has it on board, RVGS. And it claims that it combines beamforming and phase differencing to get rid of this nadir gap that was the main problem of using this system before. As you can see here, this is a picture showing a co-registered bathymetry and side scan image from the system here. It's a study made by EdgeTech, though these are EdgeTech engineers, and I believe there's some from the corporate arms too. You can see that the nadir gap is gone. But is it true? How the beamforming is doing that? How can we do that? So my research, the main point of my research was trying to discover how EdgeTech did that. So what I did, I implemented conventional methods such as the vernier that I'll show you after that, and tried to mimic what EdgeTech was doing by taking hints on their documentation that, as its industrial secret, I don't know exactly what they're doing, but I tried to see how things were working and how it improved the signal processing results. And I also was interested in see the quality of this data. So is it good? Okay, we have data on nadir, but how good is it? So I also compared co-located data sets from the two systems, the 6205 and then the 2040. So to start my presentation, here is my background, some information that I needed to perform my research. As you know, when we have two staves in an array, the phase difference between both staves, obviously depending on the stave spacing, can be derived to the direction of arrival in an estimation method. Obviously, if you depend on this baseline here from half lambda, which were the previous systems in 1980s, up to like the most modern systems that use longer baselines, we have less ambiguous as we get close staves, but they get more noisier. While if you use longer baselines, we have more accurate data because the phase curves, like the image is better, it's longer to the same amount of angles. However, it's now more ambiguous because we have plenty of solutions that we can derive from each. This is an example of the 6205 data, like just one pair of it, just a half lambda solution, which is direct, just as a CMARC did in the 1980s. You can see that it's very noisy and it's unusual for hydrography, at least like that. So the more modern systems are using this method here, the vernier, by purposely building an unevenly spaced array. They can have different patterns of phase and make them choose the phase vectors that are more aligned in this process named phase coherence. That makes us choose the right answer, even using the longer baselines. An example of this is the geoswath that was built by Geoacoustics in the past. And what do we have now? So the 6205 has 10 staves, so much more than before, and spaced, all of them evenly spaced by half a lambda. What could we do here? We could pick two pairs and make the noisy solution that I showed you before, or you can make an average of all the equidistant pairs that we have, having some improvements in depth accuracy. What we can also do is somehow implement the vernier solution. I have an ambiguous solutions already, but as I said, it's noisy. But I have 4 pairs of 1 lambda 1.5 pairs of 1.5 lambda 4 pairs, and one I have different combinations. Every one of them may yield a solution, an ambiguous solution. And what I can do, I can use the unambiguous solution to choose the correct answer for each of the pairs. It works very fine for the 1 lambda, for example, because though the half lambda is noisy, as the possible solutions are sparse, I can easily choose the correct one. However, if I went directly from the half lambda to the 4.5 lambda, as they are very tight, the noise in the half lambda may make me choose the wrong answer. So what I did, I just made it progressively. So first I got the 1 lambda solution, and then I used it to disambiguate the next one, and so on. So I didn't incur that problem here of the noise. And finally, the solution 2 is beamforming, which was the one that I implemented in this study. These are the results I have for the conventional method that I showed you. You can see here the half lambda solution, the half lambda average, and the vernier refined solution. If you look at it, I can kind of see the bottom up to 68 degrees in the first one. It's noisy, but I can see it. And half lambda average, I can get a little more of it. At about 75, maybe I can see the bottom. And on vernier, I can see it collapse at the bottom. And I have less noise, and I can see more or less up to 80 degrees. But it's very noisy still. I have to do something about the variance. What's usually done by most systems is a time average. What I can do, I can I can set an angular window around the sample I have and make an average. In my study, I used the circular mean, the complex average. However, most systems use regressions too, like first order regression, to have a linear solution there. I also implemented it, but I didn't go too far with the regression. Here we have the results for the time average. In the first plot here, we have no time average. In the second one, we see that I could collapse the data. However, I still have some noise here, as you can see. But this, we can't get rid of it just with processing, because they're shadows. Because as we have targets, shadows naturally don't reach the transducer in a direct path. So they bounce, they diffract. So that's why we have this distorted data. And the only thing we can do about it is filtering. So I also developed 2 filters. The first one, coherence, which is how much the vectors in a window are in the same directions. It's kind of an index. I picked the sum of the vectors and take the magnitude of it and divide it by the number of the vectors. So if they're very aligned, I have close to 1. If they're misaligned, I have a small sum, so a magnitude close to 0. So it's an index to show how much they are aligned. And also coherent SNR, which is not exactly like signal to noise ratio, but it's just directional. As I was doing the circular mean, I had, for example, I had sample 1 and sample 2. I have my solution as the phase average here. I could project each sample onto the direction of the phase average so that I could see how much intensity I had on the direction of my solution and how much intensity I had in the other solution. And by making a ratio, I could see how much multipath was having. So this is a result of filtered versus unfiltered vernier that I had to this point. As you can see, these are my plots. I set coherence more than a half. This was just adjustment that I did with my own data. And the SNR, more than 3 dB. You can see here that the shadows, as they naturally have less SNR because of the signal, most of the signal doesn't reach the transducer. You see here that the shadows are now rejected. However, we lost some of the 4-range data too. And now beamforming, what it is, what can we do with it? So first, my research studied conventional beamforming, which is a specific branch of it. As the EdgeTech, the 6205 is a narrowband system, I could use this formula here, which is for it's the phase beamforming, which is not less than a weighted average, as you can see, a weighted sum, as you can see here. If you pick each signal coming from each stave and sum, we have like a beam directly, a thinner beam directly facing the array. So we are changing the beam pattern for a 1 element beam pattern here, 138 half power beam width to a 10 degree half beam width, so a much thinner beam. We have two weights in this formula. The first one acting in amplitude, the second one more or less make a delay in each stave so that we could choose the direction from the signal is coming. The amplitude weight changes the pattern of the side lobes that we have here. As you can see, I applied Adolf Chebchev, which is very common in bathymetry, and reduced the side lobes to the level of minus 30. The second weight here, the exponential, is responsible for choosing where the array will be sensitive to, so without physically translating the array. And how may it help? So we don't have a multibeam here. This is the 2040. We have a 50 lambda that is capable of making a 1 degree beam. But what we have here in 6205 is just 5 lambda, which if I summed all the 10 staves, I would get at most 13 dBs shaded. So it's not a multibeam, but I was hoping that by making the beam thinner, I could attenuate this other side of the signal here coming from the other swath, so that I couldn't reject the nadir data, resulting in having better density there on nadir. The beamforming could also help me in getting rid of multipath. I have two types of multipath. The outbound that happens in the let's change one. I have two kinds of beamforming. The first one in transmission. I have two kinds of multipath. The first one I can just go by transmit beamforming, which was not on my study. And the second one, which is the multipath that comes from the reflector up to the surface and back to the transducer. I could make the beam thinner and maybe get rid of this multipath too, as you can see in this animation here. We have two pings. The green one gets interfered by the red multipath. However, when I make the beam thinner, I may attenuate the one coming from up. And the third benefit I could have from beamforming is amplifying that sonar. As I have more directivity, for example, for 138 dB at 138 degrees, I could have 24.7 dB of directivity. We can compare it by using maybe a 2-split array, using a 14 main lobe here, resulting in a 34.7 dB, which is almost 10 dB amplification, just facing the array in the transducer axis. Naturally, if we steer it, the beam gets a little fatter, so we can go from 8 dB here on nadir up to 10 dB facing the array. So, and beamforming, how can I implement it? As you can see, I can choose like 2 split arrays to make the phase difference. I need a pair at least. So I could pick 9 elements and have a phase difference between 2 vertical arrays spaced by half lambda. I could choose 7 elements, though I have a slightly fatter beam. Now I have 2 pairs, so I can make an average and have maybe better variance on that. I could pick 5 elements and have 3 solutions to average. And finally, I could combine 3 elements using 80 split arrays, 4 solutions. So I could have a little better variance. So we're basically trading here that variance per multipath suppression and SNR. This researchers here, Zoli and Yuan, in 2005, they made a study saying that the 3-element combination would be the best one, because as we have a fatter beam, we would have a longer phase curve. So in the MRA, we would have like a better linear solution, so that we would have less regression error. However, as I was just averaging and not making the regression, I chose the 9-element beamforming here, the first one. I also compared it in my thesis. I didn't put on the presentation, but this yielded better results from my algorithm. And about methodology, this was my survey location here, Odeon Point State Park. It was a square here of 350 per 250. I had rocky bottom here close to shore. I had a slope. I had a flat sea floor close to the east side. So I had all kinds of bottoms, at least simulating the depth that I would have in the shallow river. so that I could assess both systems. The depths ranged from 3 meters to 14 meters. You can see here the data sets that I acquired. I set the 6205 to plus or minus 100 meters range.
Yeah, restart the screen share. It seems to have frozen.
Okay. And I also had here the plus or minus 70 degrees EM 2040. So you can see here in gray, it's one line, how much wider is the swath. Again, this is a 5 meters depth. You can see that I got complete coverage up to 75, while on this 2040 I got 40 meters of coverage. And finally, how I implemented it in first place. As I'm sampling equally in time, I had in advance all the TWTTs I had. So if I assumed flat C4 by using the first arrival here in red, I could see more or less where the signal was going to arrive, depending on the time as the time progressed. As you can see here, I just converted where the signal was expected to come in the steering angle and beamformed it. And these are my results. You can see here in white, we have the brighter area is where we are getting more amplitude from that. So it's following as I steer the time series. So it was really working. And these wavy patterns here, these are the side lobes. It's because I didn't correct for roll here in this plot. And so far, what I had in bottom detection, this is just applying the beamforming, and this in black are the EdgeTech solutions. You can see here that the solutions are drifting from the EdgeTech solutions when we get to far range here after 50 meters. This is because I had a steering error, because in my first model, I assumed flat C4. So I was steering to the wrong place as I hadn't slowed C4. And why is that? It's because when you steer, the time series, the phase time series, is very well defined close to the MRA, the mean response axis. And when you go further from that, it starts to distort the phase averaging, and it would end up drifting the bottom solutions. So I had to somehow mitigate this steering error, and for that I first chose to recursively update depths. So I steered in steps of half a degree and processed all the samples in that interval. As I had the first depth solution, I would use it to update the next steering, so that I would kind of track the C4. And I was mitigating how the steering error from first assuming the flat C4. As you can see here, I just made it in steps of half a degree from the first samples from the first arrival to the last sample. So this was the way I dealt with the steering error, by recursively update the steering. By using this, I just applied the steering once in the time series. I just changed the angle as I was progressing with time. Another option of doing this was using fixed channels, just as multibeams can use. I was basically changing updating a recursive solution per a brute force solution. I would look at all directions at the same time by setting a fixed number of channels. And you can see here, I also implemented this by choosing the one that has the higher amplitude, because as I'm steered to some place, at least with conventional beamforming, I expect the maximum response coming from that place. The one that returned me the maximum amplitude was the channel that I used. One thing that I have to say to you is that in nadir that quite didn't work, because the water column is very important, is very significant in that place. So here, up to 15 degrees incidence more or less, I had to force nadir detection, as I was showing you before in flat C4. After that, I could just let the algorithm choose the correct channel by amplitude. So these are my results from the one that I stick with because it was more efficient. The one that's normally used, that is the fixed channels. If I had maybe one beamforming board for each channel, that would be good too. And this is a root music algorithm that's not mine, it's from one 2018. I just adapted it from my algorithm. I put it here because though it's a high resolution method, it's very costly, computationally expensive, so it's not used commonly in real time. But it's a good benchmark anyway. You can see that the solutions are very close, and now you can see that here I plotted the EdgeTech in black. The drift is mainly gone. I still have some drift here, but EdgeTech itself, you can see here that we don't have good solutions there anyway. And my results finally. Here we have two grids, the EM2040 grid, which was integrated by Chimera. This is the EdgeTech grid. You can see that it's filtered. I have in the raw data, I can choose unfiltered data. But the unfiltered data just return me zeros. So what I have is like, this is what I have. Even choosing the unfiltered data, I don't have solutions where we have these gaps. And these are my solutions, the half lambda average, the vernier, the method I showed you, and the 9-element beamforming, which was the one that I implemented. Let's look here closely to see how can we see of the morphology. We now are looking here at an 8.5 meter depth at this rock specifically. EdgeTech, it's filtered there in the EdgeTech grid, so we can see there. And you can see that this rock is about 83 degrees here in the far range. I can't see it with the half wavelength average. It's so noisy that I can't see anything after 18 meters, sorry. As for the vernier, we can see the rock here at 83 degrees, and the same with the beamforming. So you can think that vernier and beamforming may be equivalent. However, here, as I showed you, I'm averaging 30 times series, while beamforming I'm making two weighted sums. So it's 7 times more efficient doing beamforming than doing vernier in this aspect. Now, looking at the normal incidence, that's also important. It's the main point of this study, probably. We have a small square here down to the area of 40 meters per 20 meters. You can see here that the EM2040 resolution is very high. We see the edges are very, very sharp. When we compare, for example, with the EdgeTech solution, you can see that it's very smeared. Even more smeared than my solutions. You can see here the half of lambda, vernier, and beamforming. We have a more sharper version of it, probably because it's averaging more, either using a larger window or using more elements. As I said, EdgeTech uses 3-element combinations, so they have at least 8 split arrays, so they have more averaging necessarily. By comparing my solutions themselves, you can see here that this is jittery, this is noise. We can see here that the beamforming is cleaner than the other two.
John, can you go back two slides? I'm just trying to.
Yeah.
Yeah, right here. Yeah. So the white outline in the upper left figure, that's the multi-beam. That's the 2040 coverage.
This is the 2040 coverage.
Okay. Just the white box.
So this in gray is the 6205, just the line I'm analyzing.
Okay.
This in rainbow is the M2040 data.
So okay, so it's not all right. So it's just the color.
Yeah.
Sort of.
This part here it's inside the white box.
Okay.
So here we have the 2D plots of elevation, SNR, and coherence for a specific thing. You can see here that I set the thresholds 3 dB and 12 dB. It wouldn't be fair if I set the same threshold. So I set like the 90 dB separated, because as I said before, theoretically we would have 8 to 10 dB amplification by using beamforming. Even so, we can see here in the left part of the plot that the beamforming is rejecting less data in the far range. Also, we have more outliers here in the vernier. And finally, in the SNR, we can see that we're really getting this mean level amplification of SNR. But not only that, as you can see here, near nadir, we're getting even more amplification, meaning that we are being successful in attenuating some of the interference that's coming from there. If you look now at the coherence plot, we can see in the far range that the vectors are much less aligned in the vernier, meaning that we are getting that apparently good solution, but we're making heavy average and diluting the noise inside a very large window. The beamforming, however, it's filtering spatially placed data instead of diluting noise in average. So it could be considered more efficient. And not only that, as you can see, the coherence is very close to 1, meaning that I'm averaging like less signals from other places that I don't want. This is a minor result. These are secondary results, the quality assessment on the 6205 data. I made TVU target detection, density, and efficiency. As the TVU, this is an uncertainty plot, as you can see. So it's not considering the bias, the problems in draft, the problems in type, just the uncertainty between the EM2040 grid and the 6205 lines. I got special order up to 73 degrees, order 1 up to 80, and order 2 up to 85. For target detection, I looked at the grids and tried to identify these targets here, more or less 1 or 2 meters wide per half and 1 meter high, at different incident angles, close range, mid range, and far range, at 8 meter depth. And these are the 3 cases that I chose to show you here. You can see in the 3 cases that I got a smeared solution. This is a rock. It's smeared across track, and not only that, its height is also underestimated. So this is concerning for someone who is looking for very high accuracy for navigation standards. So I would say that, yeah, this is a problem. In far range, however, I got more or less the same range, but this can be explained because the multibeams itself, they may underestimate heights in this angle of incidence here at 70 degrees. Density, these are density grids. You can see here that the M2040 is the density is very uniform. This is because the 2040 has active stabilization, while the 6205 doesn't have, because it can be steered along track just as the 2040 does. So every time the ship pitches or like have yaw, we have these differences in density. And also, you can see here by looking very close at how much they are dense in fact. The red one is the M2040. You can see here that we have a long track distance between pings of 16 centimeters, and we have less in the 6205. This may be misleading, as most PMBS have really high density across track, while they may not have so much along track. And we plot them in a grid, a square grid. It doesn't show that to you, so you really have to zoom in to see. By comparing both systems here, we have, as I said, a really higher across-track density for the 6205, but for the along track, we have less than a half. That's because this 2040 is double swaths, so we can go really fast with it, and also because it's just waiting for 70-degree swath, while the 605 was waiting for an 85-degree swath. And that's affect directly the efficiency. You see here that the 2040 can get 100% coverage, even going at 22.6 knots. This may be an unreal speed, but yeah, it can go much faster than the 6205. The 6205 have to go at most at 5 knots, as is specified by the manual. Even if I didn't have this specification in the manual, it would reach up to 7 knots, so it's not much higher than that. And for order 1, it's even less because I have to use like the 8-degree swath. So it's the conclusion I get from that is if I can go at high speeds, the 6205 isn't more efficient than the Multibeam. However, in an environment such as the Amazon, we have logs, we have the moving sandbanks, and we don't want to run aground or service ship, we need to go slow. So in this situation here, where both systems are with the same speed, we can see that the efficiency is as higher for the 605 as the swath is. So it's maybe a really good option. So my conclusions finally. For the first question, how can applying beamforming and PMBS improve the signal processing results? I saw that I could see morphology up to 83 degrees while being much more efficient than vernier because I'm making much less averaging. I also had less noise in the nadir region, that both on this plot here and also on the 2D plot, I could see that I had more SNR in the nadir in the region, as you can see here. For the second question about the quality, I saw that the 605 was able to reach the standards of the EHO, even special order and more than the Multibeam Echo Sounder up to 73 degrees. I could see that it is efficient if our survey environment doesn't allow us to go very fast. And unfortunately, we saw that we had target underestimation, and if it's important to you, probably wouldn't choose this system, at least not for a special order. So I believe all in all, the 605 is a very impressive system. We have the backscatter that I didn't work with, but it's very good for target detection. We also have co-located bathymetry, and the bathymetry, if you need another one survey, for example, the rivers there, most of the surveys are the ones, even by using single beam systems up to today. So this system can be can have very better result by comparing with a single beam and a very fast result, a very efficient result comparing with the multi-beam if we're in shallow waters and running slow. And I'm happy to answer your questions if you have. And my references for this slide is just after this slide here, if you need them afterwards. Thank you very much.
Well, thank you, and actually, 30 minutes?
35.
I know people are everyone appreciates you. I think just the committee first with questions. If you just want to go around the committee, I don't know who wants to start, Larry?
Sure. I think this is just really great work. It's wonderful, more than a master's too. At least yeah. I'm gonna just start with a real fundamental question. Would you buy a 6205 as opposed to, say, a dual head?
I would, yeah. For our problem there, I definitely.
And you're not worried about the target detection issues?
So I believe knowing where the targets are and knowing that in the Amazon most of the problems are the sandbanks and knowing where they are, I probably think that we could make like a fast survey with the 6205 and maybe if
you say fast, you're saying you can't use the 6205.
Yeah, it's not fast, yeah.
So it's 5 nights or less.
Yeah, it's not fast, yeah. I maybe use first the 6205 maybe to look to search where the targets are, and if you have something that is very concerning, I probably would take probably a multi-beam and just pass there where the if it's right.
But is that really more efficient than just a single, say, dual head multi-beam survey? Where you get the answer, both answers?
You mean a dual head?
Yeah.
So
if what you're really worried about is coverage.
Yeah. So
comparing, in Germany, in the rivers, they use triple heads.
Yeah.
Boom, they cover bank to bank all at once.
We also have them in Brazil, but we also have to consider costs. So if we compare the EdgeTech, the 605, maybe we have something around $5,000, something like that. While with a dual head, maybe we would have to spend a little $2 million, something like that. So not only, just looking at the results, we probably would choose the 2040 dual head, but we also need to consider cost.
Okay, well, but again, you described a scenario where you'd come in with the 6205, but if you had targets that you were concerned about, you'd bring back a multi-beam. So you still have to have the multi-beam in the mix too.
Yeah,
the cost of that.
And
the cost of the second server.
Yes.
Okay, I'll come back.
Yeah, I agree. I think you did a great job. I have lots of questions, but I think the first one is maybe related to your conclusion slide, or actually you can go back to slide 41.
Yes.
And you made a conclusion based on this target detection.
Let's see. This one?
That one. So you're comparing the 2040 and the 6205 and saying, there's smearing, I think, in the 6205.
Yes.
But this is your process solution, is that right?
No, this is the EdgeTech.
That's the EdgeTech
Yes,
solution.
yes.
So did you compare, so is your solution in there as well?
So the first part here, sorry, before the quality assessment, I used only my solutions. But I didn't think it would be fair to compare the results, like Joe's assistant, to make a quality assessment with my algorithms, because I know they're not so good as the EdgeTech. So I used their results. So these are how they detected, not me.
Okay. I guess then my question is more on what your thoughts are on this, because I know that when you did your solution, you did a lot of averaging.
Yes.
And so my assumption is that the smearing comes directly from there. And so you have a trade-off between averaging down the noise and smearing away the things you're interested in.
Yes.
Or not doing that. And my question was whether you, particularly for this, if you explored that, because it's quite possible that that's just an artifact of how someone chose to average the data. It doesn't actually reflect anything about the limitations of the system. It's just a limitation of a specific choice in processing.
So
Do you have thoughts on that?
Yeah, yes. So in my thesis, I believe I made a comparison between the EdgeTech and my algorithms too. And there's a 3D plot at a point cloud where I showed you that my algorithms were not smearing. Like there was a rock, probably the first. I don't remember it's the first one. There was a rock, and my algorithms would really detect the minimum depth, while the EdgeTech was smearing, having the height under estimation. So I believe, I don't know what they did, but I believe that they're using a very heavy averaging, and that's why they're getting this smearing, because my algorithm didn't get it, not in this intensity.
Yeah. Okay. So perhaps that conclusion you made, or the problem you're associated with that, is resolvable.
I believe so.
Okay. All right. Thank you.
You're staring at me now. Can you go to slide 35? That one. Ooh, where'd it go? On 30. Get that back.
Back to
35. So you said you don't do as well as EdgeTech, but you do a lot better. Or at least they're throwing out a lot.
Yes, they are filtering, all of it. I also have a filtered version of it. This is my unfiltered version. This one is very likely filtered. I believe I put maybe 3 dB or 2 dB just to get rid of a reverberation that was making me upset here.
Yeah, so to get to the areas and maybe talk a little bit, if I were using the EdgeTech system, I wouldn't use their process. You say they're better, but you might be good enough just doing your own process.
Got it. Yeah, when I compared it, the EdgeTech solutions had very much less standard deviation, which also because of averaging. Yeah,
I'm positive.
Because of heavy averaging. But my data in the averaging process didn't, when I computed the confidence interval to compare it with the TPU standards, my solutions had a worse confidence interval than the EdgeTech did. Yeah, so in terms of TPU, they get there, but the price they're paying is averaging.
But less smearing.
Yeah.
So those two things go. That's the point.
And I think that was probably pretty, I guess, I look at it as it was their response to the early phase measuring sonars, which gave you such a mess that they wanted to demonstrate that as they went out to the farther ranges, they could actually give you confident solutions. So so there may be some adjustment there in terms of a trade-off.
So you've done a great job, so it's hard to actually think of questions, but a lot of work, I can tell, very well done and complete. So what's left? What's the biggest limitation? What would you do next?
Yes, so
When you come back for a PhD with John,
I'd like to, but I have to go back to the they asked me for me. So when combining the elements, I did a 9-element 2-split array. But the best option, as that those researchers said, it was using the 3-element somehow. I used it, but I just averaged the 4 solutions I had. But I had also ambiguous baselines there that I have used. I tried to, but it was not simply applying Fourier. I was getting bad results because after reading what they said, I believe I need to make a phase unwrapping in the beam after beamforming, and then using the ambiguous baselines, and that would yield me better, making use maybe 2 or 3 more time series to average there. I believe that would be my next step.
concentrate on the phase unwrapping. You probably know what it's like.
Yeah, I don't, I'm not sure what to ask, because I really think this is great. John, one of the things I asked, when you went to all this effort, you called recursively steering, basically, you worked your way through the time series and make sure you have one channel, but you kept on shifting the phase delays. And then I asked the question, why didn't you just do all the channels? And your answer was that that's more beamforming, there's more processing. And actually one of the hidden things here is it's not real-time processing. It's a nice solution, but it's not the job of our masters to do compute optimization. But if you use just an FFT beamformer, which is one chunk calculation, all the funnily spaced beams are for free. Could you describe, because you did implement it when I sort of asked the question, you said there was something negative about having all the beamforming channels there. Was there something else beyond speed? Because it seems simpler, rather than have to follow the seafloor, just wait till the seafloor arrives in the beamforming channel.
So it was mainly efficiency. I didn't notice heavy difference between both algorithms. You said to me that I could have used the FFT. Yeah, I read up about it, and I saw that if I used FFTs, I would have to choose which directions of arrival I would want, like how many channels, and the channel would define which direction of arrival I want. And my algorithm isn't limited by that, at least the FFT. I can freely, each sample gives freely the direction of arrival before it comes. And about the fixed channels I use, I believe that's just an efficiency problem. There's a second point that I would say that using fixed channels is better, because in real time you can compare, if you're beamforming each one of a board and you're comparing them in real time, you could use it just like the Multibeam use. And besides, my solutions, as they are recursive, they're not independent. I'm looking at the previous solution, and that may bias somehow the next one. I don't believe the bias is very important, but yeah, it's not independent anymore when I do it for the.
One thing we never discussed is you're saying it's, as you say, each solution depends on the previous one as you work your way through the time series. A lot of the multibeams as well have gates. In other words, it's where they think the seafloor was last time. In fact, the geoswath used to do that as well. Would you see any benefit of, in your last 5 pings, the seafloor was over there, and you're only advancing 16 centimeters per shot? Would you see any advantage of constraining the allowable elevation angle? I don't know if you understand what gates are. Basically,
it's basically doing on track, not only across track. Yes, I do. I think we could would have a better estimate of depth. For example, imagine if we have a shadow, and in this step, we're just at the shadow. What I did was, don't consider if the SNR is smaller than 12, just use the previous depth from the previous step. Maybe by using not only the cross track, but also the along track, like depths, we could have a depth to reference and not only the previous step. However, my steps are very small, for example, half a degree. If we have fixed channels, we won't have 180 channels, 180 boards to have all this processing. By doing it recursively, I could do it a very small step as I had 180 channels. And this is not good. I can make it with hardware.
Want to go around again, or?
Sure. So I got just a simple one, just a clarification for me, and then maybe a little more interesting one. Slide 40, your TBU slide. How did you actually calculate that TBU?
So let's go. 40.
40, I think it was.
So this is the simply cross check.
It was a simple cross.
What was different? It's the cross check, but what we usually do is evaluate the grid and not the raw sounds. And we usually make the cross lines as a reference for seeing if the grid is good or not. I didn't do that. I used the grid as reference because this was the M2040 grid. And then what I evaluated was the raw line, the raw 6205 lines. So what I did, I picked the 30 grid, and all the 6205 lines were crossed with the M2040 data. And this is just the uncertainty. So I imagine they do, it's not described. They make the differences and make the standard deviation. This is just the standard deviation and not the mean difference.
Because you had mentioned that it didn't include, and it was only, you implied that it was only the sounder uncertainty. And if you are comparing a grid to a raw sound, it does include.
Yeah, surely
the
it's affected, for example, by horizontal uncertainty. Yes, it does. Maybe I didn't express myself correctly. It's because we have the result of the cross check that just says special order, but that considers draft and tide, for example. And when I just analyze the uncertainty on that, I'm just considering the long-term variations that draft and tide. Just that.
Okay, now the more interesting question. Based on all you've done and what you know now, if you were to build your own phase measuring system, how would you build it?
That's a good question. I think, as I saw before, there are much more complex ways of beamforming, and
not electronically, physically. But
yeah.
You were stuck with the 6205 and its geometry as best you can reverse engineer it.
Yeah, I understand.
But you had the freedom to build your own sonar.
I would
How many elements? How much spacing?
So I probably would go for the technique. As I said, you said this is electronic, but I would first imagine what processing I would do, because some processes we need half lambda, some processes we need uneven space. Some of the, for example, the adaptive beamforming, I believe I read somewhere that it needs, if we have an array with uneven space array, we will maybe have better results than an ULA. So I first would figure out, this is maybe, obviously there's cost, but this is the technique I want to use, and then I would use that to go back and build it. But for your answer, what I would do now, the answer is I don't know, because I studied conventional beamforming, and I know that there are much more, there are infinite solutions possible out there. It's a big book from trees that with all these already processing techniques. I think I would have to study more to see what I could do, and then I would go back and build the
Good count out.
I would study more.
I think that's a great question, and I'd like to return to it a little bit. So you had 10 elements in your array for your 6205?
Yes.
If they said, we'll give you 20 elements, but everything else the same, would you take the 20 or would you stick with the 10?
Sorry.
If they said, I'll give you 20 elements on the 6205 rather than 10, would you think that would be better or worse, or the same? Would you take it? Would you rather have 20?
So yeah, it's costly, but I would have a thinner beam. Oh, but that would cause me that problem of having maybe a very short, thin beam. I would have problems regressing it. Yeah, I probably would combine plenty of them in 3 elements and have a more accurate solution.
What about 40?
I'm almost at a multibeam there.
Yeah, there you
That's
go.
what that's so that's okay. Yeah, no, I think that's the question. Like, is there, what is it that is, I mean, so can you go back to slide 35? Like what, why would you not want to just end up at a multi-beam? Like, what's the reason is it just cost?
I have to think about it. So I thought about maybe why multi-beams. I was thinking, PMBS have wider swaths, but what hinders us from using a multi-beam and have phase detections from 70 to 71? So I was thinking about. I already thinking about. I was curious. So maybe if we have so many elements, we'll just buy a multi-beam and try to have phase measurements from 70 to 85. That's what I would do to have a wider swath. And that's so many elements.
I think that's a good answer. I mean, it is more expensive, but apart from that, I think the thread ends at the multi-beam. Yes.
The Brazilian.
That's right. I have a question related to this slide too, which is, I'm just looking at the EdgeTech, and I'm compared to any one of your examples where you have much better coverage, right? And it just I'd take your beamforming one personally rather than the EdgeTech one. But what I'm wondering about, what's that?
That's what he took too.
Yeah, that's wise. What I'm wondering about though is why. I mean, EdgeTech is a company that has pretty smart engineers in there, right? And so, what I'm wondering is why is that? Why does it look so different from the EdgeTech solution to that solution? And I'm wondering about you picked a case for bathymetry, which is sort of a gently sloping bottom. It's actually not the case you're interested in, because I think you're interested in sandbars in the Amazon River. Or perhaps there's wrecks or other things. Like, I'm just wondering, is it totally fair to do just this particular comparison? Are there other areas in which your beamforming solution may blow up into a giant mess where theirs is sort of nice and steady? Or do you have? I'm just wondering about that.
So no, I totally agree with you. If I had a river very similar to the Amazon here, I would do it. Yeah, I chose this because
Disneyland, Disney World, they have the Amazon cruise.
You go down it in a log and get splashed.
No. It's a ride to the Amazon.
it's a limitation. It's just what I had. But it's sure that it's not an ideal environment. It's not the exact same thing that I would find there in the Amazon. But yeah,
Can I try a twist on Tom's question? If an EdgeTech engineer, and maybe there were, I don't know, are there free parameters in the setting up of the EdgeTech when you collected or processed the EdgeTech data that may have resulted in a different result?
so
Is that the only result that could come out? Or could you adjust things differently?
what I could adjust there was the pulse length. So maybe it's a frequency modulated system. So we're dealing with that's probably the ping rate by changing the pulse length. And we couldn't mess with power, just on and off. We could choose the thresholds, the SNR threshold I could choose. But in my as I could understand, this was filtered for 12 dB. And when I tried to pick the unfiltered data, which in my mind, maybe the threshold of 12 it's not considered when I pick the unfiltered data. But as I said, when I picked the data, even the unfiltered data was just 0. So I believe their method, I don't know if their algorithm, they just said, oh, this is the standard deviation of this, or the quality of this is so low that make it to 0 and that's it. I don't know what.
Your processing, your beamforming and Vernier processing, were done on the exact same data set, right?
Yes.
Yeah, so
Raw data.
yeah, right, exactly, yeah. So it really is, it's not a question of changing settings at acquisition. It's really is there any control over what comes out of their processing stream? Had you selected different filter settings or something like that?
Just the filtering, yeah. I can set the thresholds, but that's it. And as I said, I believe the plot with the point cloud is very interesting because I compared a rock, the same rock, the EdgeTech solutions and my solutions. I integrated them both. So I both integrated the EdgeTech solutions and my solutions. And while I was getting the top of the rock, the EdgeTech was getting this weird solution. So yeah, it's something with their method of detection.
I have kind of 3 questions. What's going on with the half lambda image? It's kind of a weird artifact where it's bright in the center.
You mean this one?
No. Yours, the half lambda on the left.
There.
What is wrong with that?
It's elevated.
So you mean that we
There's
have
a bright spot in the very middle.
Oh no, it's a gap. You mean
No.
that will work?
No. Why have the green stripe, the big green
Why
stripe?
the bright stripe in the middle?
Is that shallower?
I think the green stripe is actually
Yeah,
Yeah, that's probably the
that's correct.
Yeah.
Oh, and everything else
You
is.
see, yeah, that's correct.
Really
You can see up to 18 meters to each side. I have the same data as very here, the very nadir, and it's so noisy that I can't see anything
So
after.
you're keeping all that data, but it's actually not.
That's correct. Right.
What is the beam width? The horizontal beam width of the EdgeTech system?
So it's a 3 element. It's combined 3 elements. It's 42 degrees.
Oh, not this one. This
Oh, you mean a long track? A long track 1 degree.
1 degree. Because I think I see some. Well, it's obvious. You're going to have less resolution out on the edges. When I see you have some smearing and artifacts out on the edges.
On the edges are very, very noisy. Yeah, if you look at it at 3D, it's noisy. There's some of the drift that I showed you before.
So I have one last question because I didn't think anything else. This is an acoustics question, so it's a quiz. So if you weren't doing the beam, if you use your best verniers, but you're not getting rid of any multipath, would you prefer to go out on a flat calm day where the sea surface is perfectly flat, on a day that it's slightly rough?
Okay, I understand. If the surface is rough, I will get the multipath. However, if the surface is flat, I will get the multipath because the reflection would happen, just as the studies from before. That I even wrote on the thesis. But if I go out on the rough C4, I probably won't get so many multipaths from that.
Who wants to go out on a rough day, Tony? Just a terrible subject.
Use a rough C4.
Because they use it in the first interferometers.
They do, yeah, exactly.
And the SAS guys who don't have the luxury of
Had
10 elements, they have 2.
Actually, they had one. The second transducer was a surface.
Yeah, so they really want to go out on a slightly rough day.
I just you asked the question about why not just have a dual multi-beam. It's kind of interesting because that's NAVA's solution is the gold-plated EM2040D. And it, for anything but boulders, it is beautiful. I've driven them out to 80 plus degrees. But interestingly, the hardest object is a proud high aspect ratio system like a boulder or concrete cube or whatever. And so we say that the phase measuring systems are filtering. A multi-beam volume detection is still a filter. It's sort of looking at a phase slope or deciding on an amplitude peak, which they always do little spatial filtering. It was having trouble out there as well, interestingly. And it was actually another Brazilian Navy officer, Douglas Pereira, who implemented the BDI algorithm, and it looked better. But I think that was actually Tom's point that when you do a master's, you spend 2 years looking at one patch of the seafloor, you can always make it better there.
Yeah.
But you go somewhere else.
Yeah, that's
I'd finish with a comment, and that is, and I hope Anderson or anybody's listening, is we've had a series of naval officers coming through with very interesting theses, but you never have the time to publish this. And I think it would be a benefit for the Brazilian Navy to see at least that you were able to go to a conference to present this, at least proceedings. And that's something that Rodrigo was able to do, Aloisio was able to do. But later, I mean, I'd love to see Leo's, do you remember his water column imaging stuff? So I'm kind of hoping that, I know you'll be back in uniform and lost in training administration. I'd love to see you at one of the hydro conferences or an acoustic conference.
Oh, I have one last really basic question, and it's just my own, it'll just show my own ignorance, and I'm just curious, but on slide 3.
yeah. I'll go there.
Thank you. So I'm just curious about the Amazon, and you know, you're talking about steering out to 70 degrees, and you're worried about yaw. And I'm just wondering, what are the conditions out there? How stably stratified is it? How much yaw do you have if you're driving in a river?
So
I just don't know.
Okay, I'm perfectly understand. So it's not only the Amazon River that we're concerned about. The Amazon River is almost, it's kind of an ocean. Sometimes we're navigating there. I worked there before. We can see one of the margins sometimes. It's so wide, it's the river.
Yeah.
So there are places which are very stable, yes. And there are very sinuous rivers too. So yes, yaw would be a problem in some rivers. Either we would have to go very slow to compensate for the yawing, or go to a multibeam.
Yeah. Okay. I know that I was out on the Piscataqua River yesterday, and you know, if you hit the tide wrong, it was really hard to drive in a straight line. Yeah. So I didn't know how similar that was where you're operating.
So it isn't affected by tide because it's very far from the 10,000. Yeah, it's very far from the ocean. Maybe the last part of the Amazon River has some influence of tide, but the current is very steady in the Amazon River down. Yeah.
Okay. All right. Well, thank you. I think very interesting thesis and great presentation.
Questions, Brian? Any questions? Or even
most of the questions I had were answered through the other questions that we had. I did want to go back just a little bit about your uncertainty estimation, which is dear to my heart. So your analysis was just for the sounders uncertainties. It didn't include all the other components of an uncertainty model that do the ship.
Yes. Actually, I made, this was just a cross-line check.
Yeah.
I also modeled the uncertainty myself. I have the slide here hidden. Yeah, John said it was to bait you. Yeah, this was the model I had of uncertainty, because I had a very specific mathematical model from phase. I could use propagation of uncertainty and derive the angular variance that can easily be transformed into depth variance. It seems stretching here on nadir, but as you know, depth sensitivity is very low in nadir, so it happens.
Bit of an eye chart for me from this distance back here. What's this vertical scale there? Is it centimeters?
It's meters. No, sorry. It's angular standard deviation degrees. 95%. It's angular degrees.
Just change it to representation modes.
Maybe, yeah. So 0 to 4, 2 degree scale.
Angular standard deviation. All right, okay. So what I'm interested in is you talked about efficiency.
Yeah.
And when you did the comparison with your cross line, you said you get to special order, we'll ignore the other bits of special order, just a bit, out to about 60-ish degrees, order 1 out to about 70.
It was special up to 73. I can go to that slide.
It's probably yeah.
So, yeah.
So we have to those are overestimates of the actual angular range because you don't include the special order is not just this, it's
Yes,
the other
yeah.
components.
Yeah,
So less than this. So that being the case, it's a quite fundamental question with all these phase measurement systems is that extra swath which slows you down actually valuable? Because the uncertainty is high, the object detection drops out, the noise level grows. Are you actually benefiting from that extra swath? Practically, I mean, theoretically, sure, but practically, is that extra swath actually worth it?
I understand that. So one of the alternatives you might get in GHM is not only releasing charts, but making corridors. Maybe we instead of releasing a chart, we make a ship go down and up the river, just that, and try to get the most of it the ship can, so that we can release like just fast information on safe corridors. In that aspect, as we're not filling an area, we can maybe when setting the corridor, say up to here we have high quality data, and then we have more or less just specify the quality of each one of these, or the navigator to know, oh, if I navigate here I'm safe, but if I go out there I can, but the risks are higher. So, and as I said, they use so much single beams there. Like they still do very much single beam survey or the one survey, obviously not close to the port, but the mean of the river. So I think yes, it's worth it.
Oh yeah, I don't think there's any argument that it's better to do this than it would be to do a single beam survey. That's the question really was about. You know, if you say the center section I think is reliable, the outer wings I think are maybe not as reliable, but I'm going to put them on a chart anyway. You're paying a lot for those extra unreliable data, you know, because if you had a multi-beam, you would get them, but then they're not reliable anyway. So it's always a question for me. I think maybe you're making a case for approximate data is okay in this context. So maybe
Yeah.
it's context specific.
Yeah.
Okay. Right. Thank you.
Okay.
It should be a quick question. So I think we come from kind of very similar backgrounds. I'm interested in shallow water, sand bottom channel surveys for hurricane responses, that kind of stuff here in the US. With your model and everything, do you think that there's any benefit to target detection on objects that might be missed by the EdgeTech solution? Do you think that a proud object, say a pile or a stick or a wreck, might be detected where it might be missed just from the EdgeTech?
So you mean, I quite don't understand the question, sorry. If by using my algorithm, if it would be better than the EdgeTech, the way EdgeTech did, is it that?
Yeah, my understanding is that there's some limitations in the EdgeTech, bottom detection, on proud objects, either at nadir. And do you think that your model might benefit that at all?
So I believe so, because mine is less smeared. I have probably because I'm averaging less. So the targets were, I would say, yeah, the standard deviation is higher because I average less, but I can see more of the fluctuations.
Yeah.
So yes, I believe my algorithms would show more of the C4, like more of the morphology. If we just want to see there's something there, I would probably choose my algorithm. As you saw before, the beamformed, I got a full coverage up to 85. Obviously, it gets crappy when you get to the edges. But what was interesting is that even with the crappy data, I could see the morphology up to 83 degrees. So yeah, I could see that something's there. I think that's very interesting. The EdgeTech filtered that and you can't see anything.
That's a technical term. Crappy data.
Crappy data. Crappy data and smeared.
Term of art, so no understand.
I think actually Harry raises an interesting point, especially post-hurricane response, is you said you wouldn't address the side scan, but you know damn well it's super high resolution, or sorry, I'm a 20-year-old. Anyway, the old skunk striping model, know would that be acceptable if you had a really good image out there?
That's where I was kind of going is, obviously for those kind of scenarios, you'd be using the backscatter to identify targets. It's just, and what I would be kind of looking forward to doing in the next year or two, is this system capable of detecting those, proud objects, mast, shipwreck, piles, near nadir, even if it can't detect them, at the plus 75, range scales, could it actually detect those things near nadir reliably?
I understand your question. So for that, I would say it would need more tests because near nadir we don't have like these gorgeous shadows that we have out there. So we wouldn't see a mass wouldn't be seeing the image so well on the nadir, and also the bathymetry wouldn't. Yes, we are averaging. Imagine we are averaging a lot. We had just 1 or 2 points in the mass that it will be smeared to the lateral average there. So I don't think it would be the best.
Yeah, maybe we can talk later because that's what I would be looking into, this coming year is the capabilities of these for that exact purpose.
You have data from other areas.
GB Church needs to go to British Columbia. Wrecks and masts.
No, it's just a matter of like his algorithm is just from here.
Yeah.
So I'm just wondering if we apply to other places, different slopes, how's going to be that? So
another thing that wasn't on my presentation, by using do you remember the SNR calculation that I did? By picking just the signal vectors, I could make an image, like a filtered image, like a multibeam would do. It was, by comparing with the side scan image, it had like a greater result by comparing the side scan and the filtered average, the side scan image. So I think maybe my algorithm helps a little in the image. I can show you.
Yeah, sure.
Okay, if there's no more questions, otherwise Larry's got a plane to catch. I think the committee needs to meet. Just one more thank you, I guess, to João.
Thank you all for coming.